So let me start introducing you, even though some people have not joined, but they can see the presentation later. Okay, so good morning, good afternoon, or good evening, wherever you guys are. Welcome to this webinar on Isolator versus Zener Barriers. And Austin, it's me, Paolo Landrini. I'm VP of Sales of GMI, and Bob Johnson, who's been our guest speaker for some time. And he has a lot of, when I started, I used to say you had 30 years of experience. Now it must be 35.
Yeah, don't remind me. Don't remind me. Yeah.
So he has a lot of years of experience in the X world. He's also an instructor, a CompEx instructor, and also an ICEX CompPC scheme instructor. So he also keeps training programs to become EX certified. And he's an inspector. And as an inspector, he does a lot of checking on the plants, and he has a lot of experience and very qualified to talk about what we're going to talk about today. So let's start. Let me give you a 5-minute speech on GMI, who we are, what we do. Probably some of you have already heard me many times, but I have to do it. So GMI International, it's a company based in Italy who design, engineers, and manufacture a complete range of intrinsically safe and certified devices for automation packages such as DCS, ESD, fire and gas, SCADA, marine, and so on, used in many industrial sectors from oil and gas to food and bev. We have over 40 years of experience, and we are very proud to be in Italy, but on the other hand, we are a global company with offices all around the world, distributors, about 200 super dedicated employees. And as I mentioned earlier, we organize also functional safety, EX, and cybersecurity courses. Of course, we have many, many installations. Next, Bob. Okay, so because we make safety product, we make safety barriers, safety relays, so safety product, we take special care in manufacturing them, making sure that they are, because they provide for the safety of the plant and safety of the people that operate in those plants and live around the plants. So we use state-of-the-art technologies. We have a full product traceability. We test every single item before shipped from our factory. We offer 5 years warranty and 10 years guaranteed. Next, Bob, we have many certification, if I can remember correctly, the next slide, yes, that show our commitment to quality. So you have safety, IS, EXD, and so on, certification from global agency. We have TUV functional safety management certification up to SIL3, so SC3. Of course, we have the ISO 9000, 45000, ROS and REACH directive. We have a code of ethics and so on. We have many standards we try to follow. Lately, the last one we introduced, which is not yet here, is export control. Today, Bob, you have to be very careful where the products are delivered and who you deliver to.
Oh, yeah, no doubt.
Because there are some bad guys out there, or bad guys. Somebody says they are the bad guys. It's always debatable who's the bad guy. But anyhow, by law, you're not allowed to sell them. So these are the products we manufacture: IS barrier up to SIL3, safety relay, also SIL3 certified, with and without line monitoring. We have isolators, again, SIL3 certified, power supply, the first in the market, SIL3 certified, and a line of multiplexer, temperature multiplexer, ARC multiplexer, digital multiplexer. We also have SPDs, loop indicator, a division that does, services such as cybersecurity and EX services. And next, some of our customers, of course, the system vendor or the Mac are our main customer, for maybe B2 Yokogawa, without mentioning them all. Many EPCs, but we're also very proud to supply many OEMs which install our product onto their skid, wellhead packages or drilling rig and whatever else. They are set because of the reliability of our product. They are for example, we certified up to plus 70 degrees, so they can be installed out in the desert or in some very rough application. And of course, we are in the AVL of many end users. I believe that's it. Yes. So it is all your Bob. Before you start, for you guys, you have sent us some question. We have provided a question and answer presentation at the end, but you can also ask question throughout the box here. There is a box that says question and answer. You can type in and we can try to answer either through the webinar or at the end of the webinar. Great, Bob. It's all yours.
Well, thank you, Paolo. That was brief and outstanding as always. So thank you very much. Well, yeah, good morning, good afternoon, good evening, wherever you're located in the world. It's a pleasure to have this opportunity to speak to you. And certainly, as Paolo said, if you have some questions, please feel free to do so. And we'll be more than happy to try to answer any questions, even afterwards. If you have some things that we bring up, don't hesitate to reach out to either one of us, and we'd be happy to kind of hopefully answer your specific questions that you might have as we go through this. So obviously, when we're talking about intrinsic safety and we're talking about the benefit of one particular type of barrier versus another, let's backtrack just briefly, talk about explosive atmospheres. So when we're talking about explosive atmospheres, the concept of intrinsic safety is one of those concepts that we use as a protection concept to deal with providing electrical instrumentation equipment in a flammable gas or dust environment. So a hazardous atmosphere is what we're talking about, is basically that atmosphere in which we're going to have a flammable gas present. We're going to have that in combination with oxygen or air. What we're really concerned with is the potential ignition source. And within the relevant worldwide standards, there's a whole bunch of different ignition sources that we talk about with regards to electrical and mechanical equipment. What we're really concerned with regards to intrinsically safe is what is called the minimum ignition curve, or the minimum ignition energy, based upon the particular gas or vapor in which we're applying a piece of EX equipment, or specifically intrinsically safe. So, of course, the equipment that we use in these areas, we must have them certified for those particular applications. And that gets into an interesting concept that we may talk about a little bit later with regards to simple devices and non-simple devices and the level of certification that's required for both. So protection methods, right? Some of the real common protection methods that we talk about in the hazardous location world is things like segregation, where we're talking about encapsulating something. We may be oil immersing, right? Pressurization, a pressurized panel is a good example of segregation, where we're basically segregating the flammable gas air mixture from the source of ignition in some way, shape, or form, right? Now, containment, a very common practice, is represented by flameproof. That's one of the concepts that's considered to be containment. So flameproof is assuming that we're going to have all three legs of that triangle, if you will, in a sufficient quantity with sufficient energy. We're going to contain the explosion on the inside of a piece of equipment that's deemed flameproof. And then, of course, prevention is basically saying, look, we're not going to have ignition sources on electrical equipment or instrumentation equipment within a hazardous area. So the two most common methods of prevention are what are called increased safety and certainly intrinsic safety. And they operate in a different fashion. Increased safety is more where we would have, say, high power terminals, where we might use those. We have to have special creepage and clearance requirements. And again, where we get in with intrinsic safety, now we're talking about limiting the energy, but yet we can still have arcing or sparking type devices in a hazardous location. So we designate EXI as our concept for intrinsic safety. So what is intrinsic safety, right? It is one of the most flexible and cost-effective solutions. Now, the important thing to note, however, about intrinsic safety is that pretty much all of the other EX protection concepts are pretty much what you might consider to be standalone type concepts, meaning that you could buy a flameproof enclosure, you could buy a flameproof light, you could buy a pressurized panel, You can specify, and they're somewhat their own standalone components, if you will. Intrinsic safety is a system concept where we have to take into account what we call the associated apparatus. And you'll hear this term, associated apparatus. That's what we call basically an intrinsically safe barrier. But that's only one portion of our loop, if you will, because we also have the outgoing power or control coming from our control room, our signals going through the associated apparatus via the cables going out to the field devices. So it's a loop, if you will, that we're talking about. And we have to make sure that when we're using intrinsically safe, that we have to make sure that we follow all the parameters of what is the signal type, what is the associated apparatus that we need to use, what types of cables are we using, how we're going to be installing it, and what is our end device? Is it a simple or is it a certified intrinsically safe apparatus? And we have to take all that into consideration to make sure that we select the appropriate associated apparatus to match it, if you will. So we do call this a loop concept. And we have some other terms that we'll get into here in just a second. So where do we use intrinsic safety, right? What is the concept? It's prevention. We want to keep any energy, if you will, that can be released from that circuit from igniting the surrounding atmosphere. It is limited to low power applications. We're basically talking about 1 watt of power or less is typically what we would consider to be intrinsically safe. So what we have overrated components, meaning that there's a safety factor built into these components. We have certain isolation distances that we must maintain. We need to have this barrier to maintain that system integrity, if you will. The applications are more or less all different kinds of measurement and control processes. So the big applications could be anything for signaling, monitoring, controlling. These are all things that can be done via intrinsic safety. Every now and then somebody will, ask about, hey, I want to do intrinsic safe motor controls, or I want to do intrinsically safe lighting. Generally speaking, you're really limited on the amount of power that you really cannot do some of those types of devices intrinsically safe. So we're really limited to measurement and control devices, but transmitters, thermocouples, sensors, all of those can be basically made intrinsically safe. So here's again our picture of our loop. So we have simple apparatus and intrinsically safe apparatus. It could be one or the other, or in some cases both. We could have a mixture of 2 different types of apparatus in the field. We have our interconnecting cable, which is very important to understand the length and the type of cable when we start doing some of our calculations. And again, there's our associated apparatus. Again, this could be a galvanically isolated barrier. It could be a Zener barrier. It could be a barrier that's built in to a PLC rack card, so to speak. There's many different variations of our associated apparatus that we can run into. And these associated apparatus can be installed in a safe area, or in some cases, they can actually be installed in the hazardous area, depending on the rating of the associated apparatus. So the 2 different kinds of associated apparatus, right? There is the traditional Zener barriers, which Zener barriers are passive devices that more or less use Zener diodes to divert any excess energy to ground, if you will, any fault condition to ground. So these were the first types of barriers that were developed. And the first barriers that were actually developed was really in the mining industry way back in the mid-1900s in the mining industry. And they developed Zener barriers, if you will, specifically for mine signaling applications, because they realized that just because we may be running 24-volt DC on our signaling, we could still generate enough energy to ignite the flammable methane gas that you would find in coal mines. And we had some major disasters in coal mines based upon signaling products generating too much energy. So those were the first barriers that were developed. The original Zener barriers have been around for many, many years, have been widely used. And again, they are passive devices that use Zener diodes. Along, however, came isolated barriers or isolators, or we call these galvanically isolated. There's many different terms, and we all kind of use similar concepts, but basically, an isolated barrier is that it's similar in concept to a Zener barrier, except there is some sort of isolation component on the inside of our barriers, if you will, such as a transformer or some optocoupler, to keep fault energy to pass from a safe to a hazardous location. So where a Zener barrier is a direct connect device between our control panel, our output, and the end device, an isolated or galvanically isolated barrier has an extra step in that particular device, and it's more or less repeating, if you will, the signal. Let's see, did I move my thing? Yeah. Okay. So some comparisons. People always ask, well, what's the most cost comparative or cost-effective means of EX protection concepts, right? So intrinsic safety is considered to be, literally, when it's used correctly, it is truly one of the safest protection concepts. As a matter of fact, it is one of only 2 protection concepts that are actually approved for zone 0 applications. It certainly is flexibility. There is some associated installation cost, which is, you have to take more account into some segregation between IS and non-IS, right? So generally speaking, intrinsic safety is a great concept. From a maintenance cost standpoint, it's also an extremely, once you install it, generally you don't have to screw around with it. As a matter of fact, we really don't want people screwing around with an intrinsically safe circuit once it's originally designed and installed. Now, explosion-proof or flame-proof, from a safety standpoint, there are some potential negatives with regards to that. Obviously, bolts being left out, corrosion, those are all different kinds of things. Certainly, it has some flexibility. We can do a lot of different things with explosion-proof or flame-proof. The ease of maintenance, well, now all of a sudden we have to open up these enclosures and do all this. We do have to do lockout, tagouts. And then certainly purging and pressurizing. It is certainly a safe concept. It is very flexible. So there's some advantages. There's not necessarily one protection concept that is absolutely perfect for every application. I always tell folks when we're doing our training courses, it's like, look at the different protection concepts that are available, and then look at the pros and cons of each protection concept to better select, how you would do it. And I always treat, when I'm looking at a client's application, I always try to look at it, if it was my project, how I would be best doing this, trying to make sure that we're doing it from a cost-effective, safe standpoint. Let's see here. Okay, so we have our first poll question.
Here it is. It's about the X protection method, and the question is, what is the basic protection principle of IS? You guys can click on one of those, A, B, C, D, E, so we make sure you're still alive. Why you guys do this? We have a couple of questions. So increased safety, is prevention concept or not?
Yeah, it is actually a prevention concept. So
how about non-incentive also?
So non-incentive is an interesting one. Yes, it is also a preventive concept. So non-incentive is actually a protection concept that's recognized here in the United States, but it's not one of the protection concepts that's actually recognized within the international world. So we don't talk about non-incentive when we're talking in the IEC world. However, in the US, we talk about non-incentive, and we're basically saying that these devices are incapable, from their design standpoint, of igniting a flammable gas atmosphere under its normal operating conditions. So
if I remember correctly, non-incentive cannot be used in some, can only be used for certain area classification or not? It has limitation, no?
Yes, non-incentive is approved for Class 1 Division 2 for the
Division
United
2.
States for the National Electric Code. We cannot use that in the Division 1 area, and it's not a recognized protection concept under the 60079 standards.
Okay, let's terminate this poll. And let me show you what you guys. There are different. The majority of you answer correctly, I believe. Prevention, IS is the prevention method, right, Bob? Am I wrong?
Yeah.
I'm so sorry. And so isolation is maybe you get confused because we talked about isolation barrier, which have a transformer. But isolation is something like maybe oil immersion or right. And segregation could be something where we're talking about we're doing a pressurized enclosure or something like that. Okay. But anyhow, great. Thank you, guys. We also, as you go along, we talk about this application. Maybe you can also mention the dust also apply to this,
Yeah. So that is a question that has come up with regards to dust hazards. So certainly intrinsic safety is certainly a suitable protection concept for dust. The whole idea on dust hazards in general is what we're trying to do is make sure that any dust that might collect on any piece of electrical components, equipment, we need to be very concerned about the temperature, external temperature of the equipment itself. And we also want to make sure that no ignitable amounts of dust can get on the inside of our enclosures. So we have minimum IP ratings that are requirements for dust hazards. We also do have maximum surface temperature ratings that will be associated with equipment that's suitable for dust applications. And certainly intrinsic safety falls within that. You can.
I remember some time ago, there was quite an explosion in a sugar factory somewhere in the US, that you have dust of sugar, you think of nothing but.
Yeah. No, there's actually a great video that I just here recently saw. I thought it was actually from something that was going on in Ukraine, but actually what it was a coal conveyor, or not a coal conveyor, but it was a conveyor system for not sugar. Yeah, it was sugar, powdered sugar, I believe it was in Pakistan. Or no, I take it back. It was a coal dust, and the ignition was unbelievable. It just absolutely destroyed this entire plant, and in dust hazards. And so again, usually, not to get off the track here, but the big issue with dust is, again, collection of dust in around devices that will generate a lot of heat. So if we have a conveyor system, we have bearings get hot. That's almost immediately when you hear about dust explosions, it's almost invariably we'll deal with not necessarily electrical equipment, but it's usually the mechanical equipment, some sort of failure with that equipment. It's overheating, could be a rotor on a motor. If we get a locked motor situation, that can be a source of ignition. Generally speaking, intrinsically safe is certainly a great protection concept for dust because, again, it does limit the amount of energy, and we never get to those levels in which we're really concerned about igniting the dust surrounding intrinsically safe equipment.
Okay, Bob.
All right, so we'll move along here. So getting into the differences between a galvanic and an isolator, right? So this is, excuse me, I'm kind of getting over a cold, so if I start coughing uncontrollably, you'll know what's going on here. But this is what makes up a typical Zener barrier, what we see, right? So what's comprised of our barrier, and I'll see if I can take this out here. So you kind of see we have a Zener protecting fuse, we have Zener diodes here, and we have a current limiting infallible resistor, which we need to have these components. Those are the main components of a Zener barrier, if you will. So if we have a fault condition, right? So a fault condition could be a situation where maybe it's coming from our control panel. So maybe we have a little bit of an inrush or something like that. What will happen is that these Zener diodes, they will open up and they will divert any of that excess voltage. So say, for example, this barrier was rated at 28 volts, maximum. Well, these Zener diodes will be basically put in parallel, if you will, and allow more or less any of that excess voltage to go to ground. If the voltage continues on, and now all of a sudden we start seeing more current, more energy, that current limiting resistor could blow, or more likely the fuse will actually blow at that particular point in time. So everything that's located in the hazardous area over here has been protected by the use of this fuse, this resistor, and these Zener diodes. The important thing to note is that notice that we do have a good ground connection. So this is tied into system ground. Our ground connection must be no more than 1 ohm resistance max. Now we call this system ground. We typically call this our clean earth. That's separate from our normal earth, right? We have a separate grounding system for Zener diodes. We want a clean earth because we don't want to have a situation in which we have any what am I trying to think of? Any faults potentially coming in from dirty earth back into, if you will, our system. So that's a typical Zener barrier type principle. Now, an isolated barrier, we have a couple extra components on the inside. So we do still have a fuse, we have resistors, we do still have Zener diodes, but now we've incorporated our safety transformer. So in this particular instance, what we're actually seeing, if we have a fault condition that's coming in this particular instance, it's hitting this transformer and basically staying on this side of our safety transformer. So that fault condition isn't passed through, if you will. So a galvanically isolated barrier, if you can imagine this, right? A galvanically isolated barrier is going to be bigger. It's going to cost a little bit more than a Zener diode type barrier. But notice this right here. There is no need for a safety ground with a galvanically isolated barrier. Now, there may be a ground that we have for barriers in general. Like any electrical component, we may want to ground the DIN rail that the galvanically isolated barriers are mounted to. But in this case, we're not having to actually have a dedicated, intrinsically safe, clean earth. So that's really the huge benefit that you find with a galvanically isolated barrier versus a Zener diode type barrier. That's really the main function, if you will, or big difference. So a Zener barrier in a fault condition, right? So we have a fault condition like what we showed before. Again, we have that fault condition to ground in a non-hazardous area, but potentially we could have that fault condition to ground in a hazardous area. So this is the important reason why we want to make sure that we do have a good ground, right? We don't want to have it tied into our normal ground, but we want to make sure that we do have a good, clean earth to tie it to that's separate from our normal dirty earth, if you will. And again, in this particular situation, our IS circuit, the isolation is not required. We don't have that requirement for the safety ground. Excuse me. So here's an example of, again, how we might typically ground Zener diode barriers. So notice that there's actually a safety ground connection, and we might have a redundant safety ground because it is a requirement that we want to test to see, is our ground still maintaining 1 ohm max resistance over time, right? We may have a degradation. So the way we would actually have to test that, we'd have to remove one of the legs and test it. We don't want to test it and all of a sudden introduce a fault condition into a barrier system. So it's not uncommon to have actually a redundant safety ground. So we'll disconnect one of those legs, test the resistance on that particular ground loop, and then do the same thing on the standard one, disconnect it, and then go ahead and check it. And again, tie that into our system ground. But again, here's that situation where we could have that fault condition coming back in from structural ground into our Zener barriers. So that's really where our biggest concern is with the use of Zener barriers. Is the Zener barriers are fantastic. They work extremely well. However, it is only as good as the quality of our grounding system with regards to the use of Zener barriers. So I threw this in here as well because some people ask, what do we actually have to do when we're doing inspections on EXI installations, right? So this is actually part of what we call our initial detailed inspection. If you notice over here, this is out of the standard 60079-17 right here. So this grade of inspection, when you see a D, that means that's something that we need to be doing under what is called a detailed inspection. So if I'm building a skid package that involves, say, intrinsically safe barriers, these are the kinds of things that I need to check for, right? Are the cables installed in accordance with the documentation? Yes, 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 yes. And oh, by the way, I have to make sure my earth continuity is satisfactory. For non-galvanically isolated circuits, right? I need to check that out. So if I'm doing Zener diodes, that's absolutely what I need to be looking at. Notice that we also have to check our earth connections, maintain the integrity of the type of protection. Have we intrinsically safe circuit earthing is satisfactory? Insulation resistance is satisfactory. These are all things that are requirements before we put this equipment into service. So sometimes people use intrinsically safe and they're building it as part of their packages, right? But this has to be done before this equipment is actually put into service. So it's important to understand this. It could be done at the OEM level or it could be done at the end user level, but at some point in time, it needs to be done. So just to summarize a little bit here, galvanically isolated, again, no safety ground requirement. Better overall accuracy, lower installation cost, right? Signal standardization. Again, it does allow the use of grounded or poorly isolated sensors. The Zener dedicated safety ground, right? There are those routine checks. The field sensor must be isolated. There are some accuracy with regards to Zener leakage, if you will. So, there's pros and cons of each, right? And again, from a pure cost standpoint, galvanically isolated barriers generally are going to cost more than a Zener barrier. But you have to take into account what are the things that I'm trying to do. The total installed cost, usually galvanically isolated, is a better way to go. But again, certain applications may make more sense to do it one way or the other.
Okay, we have another poll.
We have another poll.
Okay, guys. Well, while you guys have opportunity to answer this question, which is a dedicated low resistance ground requiring galvanic isolated barrier IS installation? Be careful, read the question before you answer. I want to say that it is true that in the past, Zener barrier were less expensive than isolated barrier. Isolated barrier used to be size-wise, huge. Today they are compatible in size to Zener barrier. In fact, sometimes they're even smaller because we use multi-channel. And even price-wise, the difference is not that much. Oh, you have a couple of barriers there, Bob.
Yeah. I wanted to show because some people, and I apologize if hopefully you can see this, but what you're seeing here, this is a GMI product. Both of these are GMI products, right? But one of the issues that people have always had with galvanically isolated barriers is that they think they're always, pretty substantial, right? The width, in this particular instance, this width of this barrier is about 25 millimeters. And then this is the more recent generation, right? So this is the what is this? The 1000 or
5000, and it's 12.5 millimeter.
Right. So now we see, obviously it's you can kind of see it's a little bit taller, than what we might see, but generally inside of a panel, we more or less will have additional space going this way, hopefully. But what we're trying to do is minimize the space and the density on the inside of panels. So the good thing is that now galvanically isolated barriers are actually no more wide, if you will, than a lot of Zener diode barriers.
Yeah, and you have multi-channel in there. You can have 2 channels, right. Sometimes 4 channels. And keep in mind that if today the Zener barrier were to be recertified, because the advantage of these items that have been certified 30 years ago, probably size-wise they will get bigger. Because today the standard demands are a lot more stringent than they used to be. And
Yeah.
you use a lot of cooling path to reduce the internal temperatures, and even for isolated berries, So,
Yeah.
so sometimes isolated berries seems they are growing a little bit, and the Zener berries seem to remain the same size, but only because they've been certified. They don't change, And once it's certified, it's certified, Anyhow, let's end this poll, and okay, you guys, after I give you a hint, answer correctly. Yeah, because it's a tricky question. Isolated berry do not require a grounding. That is the main advantage. Really, it is the main, and more than an advantage of cost, the cost of running the ground, because it has to be a separate ground, right, Bob? You cannot just ground it to the panel ground.
Right.
You have to run an independent ground. Is that how difficult it is to keep that ground less than 1 ohm?
It
I don't know.
depends. Yeah, it depends. If we're talking an onshore application, and it's generally not going to be that terribly difficult to do that. We might have to oversize our conductor a little bit depending on the length, but onshore applications, we can generally do that. We'll have a dedicated IS earth with an earth rod, driven in outside of, say, a control building or something like that, separate from our normal earth. When we get into the offshore applications, now we're talking about a whole different set of animal here, if we will, because obviously everything is tied into a steel structure of some sort. So generally speaking, for the offshore market, most people have really shied away from Zener diode barriers because of the fact that it's almost impossible to basically get a clean earth, if you will. So it can be done, but it's somewhat difficult.
And later on, Bob, we are talking about the difference between EXIA, B, and C. I don't remember.
Yeah, I think we do, but I'll answer. We had a question here. Is there a difference between EXIA, IB, and IC? Is there a need of a Zener barrier or galvanically isolated for an EXIC loop,
Yes,
if you will, for zone 2? And yes, the answer is yes, you would.
But for zone 2, you don't need a Zener barrier, honestly. Or a barrier, no? Am I correct? You can use a different concept, such as non-incentive or...
Well, yeah, it depends. So there are barriers that are single fault tolerant, if you will. So the difference between a barrier that is suitable for EXIA, if you notice that slide that we had that showed the 3 Zener barrier or Zener diodes, right? That is an IA barrier. If we had 2 Zener diodes, that would be considered to be an IB. If we had a single Zener diode, because there is no redundancy, that's considered to be an IC barrier, if you will. Now, most manufacturers, the cost of the Zener diode is so insignificant in the cost of the overall barrier that they just more or less make a barrier suitable for IA, and then people will take those and use those for IB and IC applications. But if we are using intrinsically safe for zone 2, we must have some sort of means of protection if the end device requires protection, right? If it's a certified device or a simple device, we still have to provide some sort of protection. Now, again, you will find things like DCS cards, PLC cards that will actually have intrinsic safety built in. So you need to go back and check. I mean, if you look at a Siemens PLC, some of them will actually have a zone 2 rating, and they've built, if you will, the IS protection inside of that card itself. So there are.
I think later on, as we talk about the entity concept and how a loop has to be safe, maybe we get into this. But basically, XIA is suitable for zone 0, if I remember correctly. Right, whereas a B, it's only for zone 1. But in the US, having div 1 and div 2,
it's a different.
You need an EXIA barrier for div 1. Is a mandatory requirement?
Yes. Yes. So let's end this presentation.
Oh, okay. Here we go. So we are at the end of this presentation. So then we had a lot of questions. that let me put this aside. Let me try to manage that. I will still have some time.
Yeah, do you want me to bring up the Q&A?
Yeah, no, I can manage. Let me see, Bob. I have to give it one shot at it. Presentazione PowerPoint. I need to make sure to pick the right one. This is the only question. I have, let me see. What do you see?
Yes.
I think I got it right.
Yeah, you did. There you go.
Okay, so now I need to find the presentation, but where is it? Here we go. Okay, so you guys ask questions throughout the registration process, and some of them will reply to the answer you have posed through the webinar. So for example, the first question was multiple barriers wired in series and parallel. Make calculation for it. Okay, that's an interesting question, Bob.
Yeah. So this comes up every now and then. So where do we find this information? This is in the 60079-14 standard. This is the design and installation standard. It's in the IEC version. It's in the EN version. It's all over the place. So we need to take into account on the associated apparatus the values of capacitance, inductance, and power. So we can do summation of voltages, summation of currents, or the summation of voltages and currents. So what we've done is just on some of the other slides here, this is actually a single supply associated apparatus. So we have, in this case, our associated apparatus. The output could be 28. Oh, there you go. Yeah. And that's two supplies in a series connection, right? So sometimes you'll find, a multi-channel barrier in which you're using the output from two different outputs, if you will, to increase the amount of voltage or current to make sure that you're able to operate the end device, right?
Yeah. So Bob, while we are at it, maybe there was a question earlier on, and maybe we should explain something, that an associated apparatus, the barrier, and the field device or the intrinsically safe device somehow, need to be. We need to match. The question was, if I have an IS device, which is safe in the in the hazardous location, why do I need a barrier? I mean,
right.
To something like that.
Right. So if you look at it, so we didn't really talk about this, but a simple device and a certified device. Right? Well, actually, we may have this.
Here we go.
Yeah. So here we have an associated apparatus. We have over on the right-hand side, we have our intrinsically safe equipment. So what we have here is that our associated apparatus, it's designed, the output is 28 volts. It's going to provide 93 milliamps of power going through this device. So we need to make sure our checks, if you will, on our input, on our intrinsically safe equipment over on the right-hand side, that we don't exceed the maximum parameters of that device. So for example, the output may be 28 volts from our associated apparatus. Our device will say the maximum input we can take with this particular device may be 30 volts. So we say, okay, we're below that, that's okay. There's a whole bunch of these checks that we take into account. These are what we call entity parameters. So there's entity parameters for the output of the barriers, and there's entity parameters associated with the intrinsically safe apparatus as well. The other thing,
later on, I think we have some example, but basically, the transmitter there, whatever it is in the field, it says I am safe if you provide me no more than say 30 volts, because of course, if you send 380 volts, the thing is going to melt or get too hot. And beside the barrier, there's something that protects the wiring also. So, the maximum energy through that barrier will never be sufficient to ignite the mixture of gas present. So
right.
If you don't put the barrier, then you can connect it to a 24-volt source, which you say is safe, but you don't know, because this 24-volt source may be powered by 250 volts, by connect to a PLC, and eventually full fault this high voltage and high current can go down to the field. So let's see
Right.
if we have another question that maybe comes to that. Exactly that question. Please explain
Yeah.
about entity concept. Okay, it is a little bit more about entity concept.
Right. Yeah. And the one thing to kind of highlight too, just as kind of an overall to get your head around intrinsic safety, for those of you not as familiar with it, think of it this way: under a normal circumstance, right? Say if we have a 24-volt circuit, and a 4 to 20 milliamp signal going between a card and our device in the field. Under normal circumstances, we're never going to have any issues, right? So the barrier itself will just sit there. It's just not doing really anything. It's just basically, in the case of a Zener barrier, it's basically quiet, if you will. On the case of a galvanically isolated barrier, all it's doing is just repeating that signal back and forth, back and forth, back and forth. The point in which barriers actually really do their job is when we have a fault, we have a cut in the cable, we have a short, we have something that's out of the ordinary. That's where the barrier comes into play. Think of it like almost like a surge suppressor for your house, right? Under a normal circumstance, surge suppressors just sit there. They allow current to flow and everything else. But then as soon as we get above a certain threshold, they kick on, and that's when we start getting protection. Same thing holds true with IS barriers. So there are some things to keep in mind: simple devices and intrinsically safe apparatus. Simple devices do not require certification. So things like thermocouples, RTDs, switches, resistors, those are all examples of what you would call simple devices. So they don't generate or store those parameters. So if you think about it this way, a thermocouple that we could use for a zone area does not require to be certified. We can use a standard off-the-shelf, industrial, commercial thermocouple or an RTD or a switch. Now, the things that can store energy, right? Things like transmitters, valves, proximities, some of those types of items, if they can generate and store power, storage of energy, then those particular devices do require certification, right? And then, of course, finally, the associated apparatus, that is our intrinsically safe barriers. Those also require certification. So
here is example of the parameter mesh. So basically, the associated apparatus has to guarantee that the maximum voltage and current and energy that we transfer is below that is acceptable. It's about how the device in the field has been certified, because you can go in the, you have your transmitter, for example, you go in the certification, you say, I want to certify this at 30 volt. So they check everything at 30 volt. You can say, I want to test it at 20 volt. Then they certify 20 volt. And then whatever is selected, of course, there are some reasoning behind it. Then you have to guarantee that you stay below that voltage, because otherwise you don't know what's going to happen. Maybe it is still safe, but it's not been, tested and certified.
Right.
It sounds complicated, right? So we have a tool, an online tool that allows you to do these checks. And I know also these are part of your, in our other webinars, you always talk about this document, what is it called? DSP?
Oh, DSD. Yeah,
DSD.
descriptive system document.
So in DSD, you have to provide this type of documents, right?
Right.
Something like that.
Yeah. So basically what you do, you plug in the information. This is the loop verification tool. And what it's telling us, and what you see here, which is kind of interesting, down at the very bottom, you notice that depending on the particular product, right, and depending on the potential gas group, because a lot of the parameters are actually the same, because we're using the same barrier, you notice that in one case, the length of cable is limited to 677 meters, but in the other case, we can use a cable length of up to 5,700 and so forth meters. And the reasoning for that is that we actually have more stored, the longer the length of cable, if you will, now we have increased storage capacitance and inductance with the cables. So depending on the gas groups, right, depending on the curves, then we could have variations. We always have to make sure that we take that into account, right?
Yeah, we have to verify what area we're looking at, the air classification and the gas group we are looking at, because different gas group have different maximum energy that you can transfer. Okay, let's see if we have a quite interesting, there's more example. We have, before we answer, we have quite an interesting questionnaire. I don't know if you want to answer that online questionnaire.
Oh, yeah, I saw this one. Janet, I tell you what, let's do this because it's a little bit more involved. We'll answer this one offline, but I've got your contact information, and hopefully we'll be able to answer this one for you. So thank you for the question.
We also have a question that says, an RTD certified as EXC, can it be connected to an IS circuit?
Yeah, you could. I mean, an RTD is actually, if you go back on the slide, an RTD is considered to be a simple device. Yeah. So, and actually, here's an interesting question that has come up, and this is actually a little bit unique, but one of the things that you see with a lot of EX equipment, somebody might, for a thermocouple, you might get a thermocouple head that will be in a small little EXD housing. And somebody will buy that thermocouple head from a manufacturer that makes EXD housings. It'll have a U certificate at the end of it, meaning that it's only a component. Well, the 60079-14 standard tells you I cannot install a component certified product in and of itself. So we've had some instances where an inspector or the regulator is saying, hey, you can't do that. So the solution is actually remove that label, and treat it as a simple device, put a label on there saying this is a simple device and it's being protected by an intrinsically safe barrier upstream, and therefore we'll create a DSD for that, and there you go, Mr. Customer. So
great. Okay, so we had a generic question said if isolated barrier versus Zener barrier is just grounding, or if there is more to it. I believe I put this answer together myself, or have you, Bob? I don't remember.
No, I can't remember either. Yeah.
But there are some other differences. Beside the direct cost comparison, item to item, you have typically in favor of Zener barrier. But if we look at the total cost of installation, typically isolated barrier comes out on top. We also size, you have to measure size. There's one instance where Zener barrier really take the advantage of isolated barriers. Then when you do not isolate a barrier, they have their only disadvantages. They need to be, because they're an isolator, they need to be specifically designed for that application. So if you want 420, you need a 420 milliamp barrier. You cannot use a DI barrier in a 420 loop. It will not work, because it's there is electronics into it. So you take a 420, you digitalize it, you put it through the transformer, you recreate 420 and so on. A Zener barrier doesn't do anything. So it can be used in application that you cannot find an isolated barrier for. For example, there are some out there. We run into some instances in the past. For example, AC. I remember once there is electrodes they use in water to do electrolysis in a hazardous application, and no isolated barrier designed for that, so you can use a Zener barrier. That's the real advantage of a Zener barrier. Let's see if we have any other questions before we come to the end. How do I connect the safety ground of a Zener barrier? Well, here we go, Bob. This is all yours.
Well, and this kind of just shows a little bit kind of what we talked about. Notice that the Zener barriers will be mounted still on a DIN rail, but the important thing to note here is that in the way you can kind of tell the difference just by looking at a barrier, whether or not it's a Zener or a galvanic, is typically you're going to see those little earthing tabs on the outside of a Zener barrier. But realize that the earthing of that safety ground is also grounded straight into our DIN rail. So it's important to understand that if we're taking that DIN rail and we're mounting it inside of an enclosure, and that enclosure might be a metallic enclosure, we need to make sure that we're using isolated standoffs for that DIN rail, as opposed to just putting it on standard DIN rail where we might have clean earth or something, or non-clean earth. So we have to be very careful from our installation of Zener barriers inside of panels. It's something that usually most people will get right, but sometimes we'll do some inspections and we'll see that the Zener barriers are actually installed on DIN rail right along with everything else. And so therefore we've kind of violated our clean earth issue, right?
Right. Okay. Do I have to keep the IS and non-IS wiring separate for isolator or for barrier? I believe for both are the same answer, right, Bob?
Yes, yeah, there is a required segregation between intrinsically safe and non-intrinsically safe. I put down question marks here, but basically, if anybody is on the top of their game, they would know that that distance between intrinsically safe and non-intrinsically safe is 50 millimeters. So
well,
that,
in fact, Bob, before you do, well, you give it away. There's a problem
okay.
coming up. Yeah, it's okay. No issue. We are running late anyhow.
But here's the other thing. People, that's obviously inside of the barriers, or inside of panels, excuse me. But then also you have to be concerned about the cables that are running into your panels, right? Mm-hmm. So we have to make sure that we keep a 50 mil separation between IS and non-IS cables exterior to our panels, unless, and this is an important point to remember, is that we can separate it by a physical 50 mil separation. We can separate them by the use of partitions inside of cable trays. Or if one or both of the cables are armored or shielded, then we can put IS and non-IS cables right next to each other, right? So there is some exceptions to that 50 mil separation between IS and non-IS. But on the inside of panels, we want to keep a minimum of 50 mil separation. And this is to keep the inductive currents from traveling from the non-IS into the IS side and interfering it.
Yeah, and that was the question, but we give it away. It's 50 mm. And here are some example of incorrect example, I guess, of wrong segregation, no?
Yeah. So we don't, on the left-hand side where we see loops, service loops on the inside of a panel, that is a big no-no. Obviously, the picture in the middle where we have some IS on the right-hand side and non-IS, that's a big issue. We have a separation on the right-hand side with those intrinsically safe barriers, but the problem is then all of a sudden the cabling was run to entries that were right next to power conductors. So we violated our 50 mil separation.
I think it's the main issue with IS this is the main issue. You have to make sure that the cables are kept separate.
That's
Anything
right.
else is a lot easier. So can I install a barrier in a classified area? Either zone 1 or zone 2 or div 1, div 2. Here's an answer.
Yeah. Yes, we can. Most barriers that you will find are rated suitable to be installed in a zone 2 area. But if we need to go into a zone 1 area or division 1 area, then we typically can take those associated apparatus and put those inside of other protection concepts. So a flame-proof box, a pressurized cabinet. This is also a solution if we had those issues where maybe that cable length is really an issue for us. We can't, we're limited maybe by our cable length based upon the inductance and capacitance. So we might actually have to take the associated apparatus barriers and install them closer to the field device in order to make sure that that loop falls under the entity loop parameters.
Yeah, we have had this instance, I remember a couple of times already, where the application is already, the cables are bought and they actually lay down already, and they're 700 meter long, and the maximum distance is 1. I said, well, just move the barrier close. This the only
Right.
Okay. There was some question about IS and seal. It is not, today we sell a lot of, I would say every single manufacturer of IS barrier rates their barrier for seal 2, seal 3, and it is the standard, de facto standard, but in reality it's not a need, you know, you don't need to certify barrier for
Right.
it needs to be certified for you know, depending where IECX, ATEX or UL or FM or whatever else. But for sure a sealed device is typically has some advantages over a non-sealed device.
Yeah.
And they will at least
yeah, I think, you know, where it would be actually, you know, well, if we have a fire and gas system in which we need to comply with the functional safety requirements, right? Then certainly having a SIL rated product as part of that overall system, absolutely. You know, is it a good idea to have it for other applications? It doesn't hurt, right? It just means what we're talking about here with SIL ratings is that the reliability of our products are basically validated. That's really the whole thing.
Yeah.
So,
but in oil and gas today, you know, most of the applications that require some kind of SIL rating. So, and if you are in oil and gas and you are using IS, then a barrier is a mandatory requirement. So that's why you find them all certified. We have SIL3 barrier as well as SIL2. We are running to an hour, but if you guys stay along a little more, we have a few more questions.
yeah, I think this was that question that we kind of addressed, I think, earlier.
Yeah. So zone 2, yeah, we answered this question. When we use ISB for control system output signal, why would we use an ISB on control system input signal as we use IS field device? But this must be the same question we have answered also, right?
I think so. Yeah, I mean,
it's actually very similar. That was posed live. Basically, you need a barrier, you know, regardless. Even if we have IS certified devices installed in the field, they still require certified ISB for input signal and output signal for the controller of the end device. While we are mostly concerned with the energy being limited to the device due to fault or other situation, we treat it as a loop and don't want fault traveling into the safe area as well. Traveling into the hazardous area, no?
Right. Yeah. I mean, traveling into the hazardous area, but
maybe mistaking our answer. Great, guys. We are running to an hour, exactly an hour. We have one last poll for you guys. Let me see if I can launch it. How did Bob do? I need to change the name of this poll. How did Bob do?
Oh, you did a lot of it today, Paolo. Thank you.
Okay. Nessuna domanda aperta. You have that answer on, you know the answer, the answer you want to send by mail, right? You have the question, I mean.
Yeah, as a matter of fact, Janet, if you could drop us an email, because I don't know if I'll have it.
I have it here. I will.
You have it? Okay.
I will copy it and send it by mail. Okay, great, guys. Thank you for being with us, Bob. Thank you for participating. You will receive a certificate of participation as well. You'll be able to review this. You also will receive the copy of the slides, and you will. Let me show you this. And you will be able to view the webinar once again on our YouTube channel. So, interrompi condivisione. In my Italian mood already, you know what time is that? It's only 4 o'clock. Not bad. You got still a day of work ahead, right?
Yeah, we got a full day. So, and by the way, there's other videos that we put together or presentations on other topics. So,
yeah,
you know, if you want to waste some time on YouTube, check out some of the other ones. Let us know what you think. You know, we always appreciate that. We've had some good topics over the years and been doing this for a while now. So we're going to come up with some other topics, hopefully for 2023. If you have any suggestions or ideas that you'd like, please let us know. We're always looking to try to put something that it would be relevant and valuable for your business and obviously for your colleagues. So don't hesitate to let us know.
Great. Thank you again. And goodbye. Let me see if I can close.
All right.
Ciao, Bob. Ciao, guys.
Ciao, Paolo. Take care, everybody.
Ciao, take care.